If you want serious aviation investigations without speculation or conspiracy noise, subscribe now, because what you're about to hear is not theory. It's math, physics, and a reality most people don't want to accept. On March 8, 2014, Malaysia Airlines flight MH370 vanished from civilian radar with 239 people on board, and in that moment, the modern illusion of total global tracking was shattered. The aircraft was a Boeing 777, equipped with multiple communication systems, redundancies, and tracking protocols designed to prevent exactly this kind of disappearance. At 1:19 a.m., the co-pilot transmitted the final routine message to Kuala Lumpur Air Traffic Control. "Good night, Malaysian 370. Minutes later, the transponder stopped transmitting, and the aircraft's digital identity disappeared from civilian radar screens without a distress call, without an emergency code, and without warning. Military radar later revealed that the plane did not continue toward Beijing, but instead made a deliberate turn back across the Malay Peninsula in controlled flight. For nearly an hour, MH370 crossed Malaysian airspace in complete radio silence before heading northwest over the Andaman Sea. Then it vanished again. Days later, investigators discovered something that changed the scale of the mystery entirely. Although communication systems had been disabled, the aircraft continued sending automated satellite handshakes to the Inmarsat network for almost 7 hours after takeoff. These pings did not transmit position coordinates, but they allowed engineers to calculate distance arcs based on signal timing and Doppler shift analysis. From that data, two massive corridors were drawn across the globe. One stretched north across Central Asia. The other extended deep into the southern Indian Ocean, one of the most remote and least accessible regions on Earth. Radar evidence eliminated the northern path. Fuel endurance calculations narrowed the window. By the time the final satellite ping was recorded at 8:19 a.m., the aircraft was almost certainly far south of any populated airspace. And that is where the problem begins. Because while the satellite data appears precise, it does not give a point on a map. It gives a curve, a vast arc stretching across thousands of kilometers of open ocean. Somewhere along that arc, fuel likely exhausted and the aircraft descended. But even under ideal assumptions, that arc still represents an enormous search area in one of the deepest parts of the planet. The world believed that with satellites, sonar, and modern computing power, any aircraft could be located. MH370 proved that belief was wrong, and the deeper investigators looked into the data, the more they realized something unsettling. The reason this aircraft may never be found is not mystery, it is scale. At first glance, the satellite data looked like a breakthrough. Engineers used handshake timing and Doppler shift calculations to determine the aircraft's distance from the satellite during each automated connection. But distance is not location. Each satellite ping created a circular arc on the surface of the Earth, representing every possible point the aircraft could have been at that exact moment. By the time of the final handshake at 8:19 a.m., investigators were left with what became known as the seventh arc. That arc stretched across a massive portion of the southern Indian Ocean. It did not show direction, it did not show altitude, it did not show whether the aircraft was gliding, descending, or under control. It only showed distance from a satellite positioned thousands of kilometers above the equator. Even small uncertainties in timing calculations translated into enormous horizontal error margins across open ocean. A deviation of seconds in signal modeling meant tens of kilometers of positional uncertainty. Wind speed assumptions added more variables. Fuel burn modeling introduced further estimates. The final possible impact zone was not a point. It was a corridor hundreds of kilometers long, and that corridor lay above ocean depths exceeding 4,000 meters. Search planners had to convert mathematical arcs into physical coordinates. They layered drift models, ocean current simulations, and aircraft performance assumptions to narrow the field. But each layer depended on assumptions about the aircraft's final state. Was it controlled until fuel exhaustion? Did it enter a glide? Did it spiral? Each scenario shifted the predicted debris field. Each scenario expanded or relocated the search zone. This was not a treasure hunt with a map. It was probability mapping across one of the largest empty spaces on Earth. The illusion of precision created public confidence. Graphics showed clean arcs and defined search boxes. But beneath those visuals was statistical uncertainty measured in hundreds of square kilometers. And in deep ocean searches, a few hundred kilometers might as well be another continent. The data did not fail investigators. It simply was not precise enough to overcome the scale of the planet. And that distinction is critical. MH370 did not disappear because technology failed completely. It disappeared because partial data in a vast ocean is not the same as certainty. Even after the search zone was narrowed to the southern Indian Ocean, another reality became unavoidable. This was not just open water, it was one of the most remote and least mapped regions on the planet. The ocean floor along the 7th arc drops to depths exceeding 4,000 meters, with underwater mountains, ridges, trenches, and shifting sediment fields that complicate sonar imaging. Unlike coastal waters, this region has violent currents, unpredictable weather, and swells that can suspend operations for days at a time. Every search vessel operating there faced logistical constraints measured in fuel range, endurance, and seasonal weather windows. Autonomous underwater vehicles were deployed to scan the seabed using high-resolution sonar. These machines travel slowly, methodically, mapping narrow strips of ocean floor during each descent. At extreme depths, even small navigation errors can shift a scan line by hundreds of meters. And when you are searching across tens of thousands of square kilometers, those margins accumulate rapidly. Search teams completed multiple large-scale operations between 2014 and 2018. Vast sections of the seabed were mapped in unprecedented detail, yet no confirmed main wreckage was identified within the designated priority areas. Critics argued the aircraft must lie outside the scanned zones. Others suggested the modeling assumptions were flawed. But even expanding the search area multiplies cost and complexity dramatically. Each additional 1,000 square kilometers represents weeks of scanning time. Each scan line consumes fuel, crew resources, and equipment lifespan. Unlike land searches, there are no visual markers, no roads, no aerial vantage points. Everything depends on sonar reflections interpreted through software models. If wreckage lies in steep underwater terrain, it may be partially buried or obscured by geological features. If the aircraft impacted at high speed, debris may be scattered across a wide field, blending into natural seabed clutter. Black boxes emit acoustic pings, but those signals fade after approximately 30 days. By the time the primary search reached deep ocean zones, those pingers were long silent. Without active signals, detection becomes entirely dependent on imaging. And imaging requires passing directly over the target with precise sensor alignment. Even with modern equipment, coverage is not instant. It is incremental, slow, measured in grid patterns across emptiness. Then there is drift. Confirmed debris found along African coastlines proved the aircraft entered the southern Indian Ocean. But ocean currents over months and years distort backtracking models. Small variations in wind or wave behavior compound over long distances. Reverse calculating an impact point from drifting debris is not exact science. It is probabilistic reconstruction. Every factor returns to the same obstacle. Scale. The search area is vast, the depth is extreme, the terrain is complex, and the available data, while scientifically sound, does not collapse uncertainty to a single coordinate. This is why, even after years of effort and hundreds of millions of dollars, MH370 has not been conclusively located. Not because no one searched, not because technology failed entirely, but because the intersection of partial data and planetary geography creates a search problem bordering on the impossible. And until a precise impact point is identified, the ocean keeps its silence. By 2018, after years of coordinated international effort, the official underwater search was suspended. More than 120,000 square kilometers of ocean floor had been scanned. The largest and most expensive aviation search in history had produced no confirmed wreckage field. Private companies later offered renewed search proposals, arguing that updated drift modeling and refined data analysis might narrow the impact zone further. But even refined models still depend on assumptions about the aircraft's final behavior. Was it gliding under control at fuel exhaustion? Did it enter a rapid spiral descent? Did it break apart on impact? Each scenario shifts the probable debris field by dozens, sometimes hundreds of kilometers. And in water thousands of meters deep, a small miscalculation becomes a permanent blind spot. Debris confirmed along African and Indian Ocean coastlines proved one thing with high confidence: the aircraft ended in the southern Indian Ocean. But those fragments do not reveal the precise coordinates of impact. They only confirm the region. The flight data recorder and cockpit voice recorder remain unrecovered. Without them, the final minutes exist only as modeled probability. And that is the core reason MH370 may never be fully found. Not because the world stopped searching, not because governments refused cooperation, but because the search area, even when narrowed, remains vast beyond intuitive understanding. The ocean floor is not a flat surface. It is a landscape of ridges, cliffs, sediment drifts, and geological noise that can conceal debris within meters of a scan line. Modern sonar is powerful, but it is not omniscient. Coverage is statistical, not absolute. And once acoustic pingers went silent, time became the enemy. Every year that passes reduces the likelihood of detection. Equipment changes, funding priorities shift, weather windows close. Meanwhile, the Indian Ocean remains unchanged in its scale and depth. In a world of satellites, live tracking, and real-time global communication, MH370 exposed an uncomfortable truth. Technology can calculate arcs across the globe. It can model fuel burn and Doppler shift with precision. But it cannot compress the size of the ocean. The final resting place of MH370 likely lies within a mathematically defined corridor. Yet that corridor stretches across terrain that humanity has barely mapped. Until a breakthrough in data refinement or search technology emerges, the aircraft may remain where it settled, 4,000 meters below the surface, beyond light, beyond reach. If you value investigations grounded in evidence rather than speculation, subscribe and follow the channel. Because some mysteries endure not from secrecy, but from scale.